to introduce Alexa Villaume. She is a postdoctoral fellow at the Center for Astrophysics at the University of Waterloo. She's been there since 2020 after graduating from UCSC in Santa Cruz with a PhD thesis advised by Jim Brody and Charlie Conrad. And today, Alexa will tell us about extragalactic archaeology. I know very little about the topic, so I look forward to learning more about it. Take it from here, Alexa.
Thank you, Omar, and thanks everybody for showing up here. It definitely is a great feeling to be in person and a little unusual, but it's good. But excuse any rustiness on my part in being in person. So yeah, I'm going to be talking about extragalactic archaeology, and the goal of extragalactic archaeology is to understand galaxy evolution. And the reason why now is a very interesting time to be thinking about this is because both observationally and on the theory side, we're at this very interesting new resolution regime. So what do I mean by that? Well, historically and still to this day, there's been really it's been really distinct galaxy evolution as we can understand it from the Milky Way, and galaxy evolution as we can understand it, outside of the Milky Way in the local group. And that basically all has to do with the fact that the Milky group and our nearby neighbors, we can resolve individual stars. And so, we get great things like this, like the Gaia data, and and so we're getting this very detailed understanding of the structure of the current Milky Way. And then with surveys like Lamoste and SDSS and models developed by people like Wang and Tang, now we're getting to a point where on the Milky Way side of things, we're actually able to recreate where all that structure came from. And on extragalactically, it's been a very different story historically, because we cannot resolve those individual stars. We have to deal with integrated light observations. And I just want to walk through and give a very brief, very abridged, almost chronological little history of how we've understood extragalactic systems historically. So, pre-stellar population synthesis models, the way we understood the galaxy population outside of the Milky Way is through, mostly photometry, shapes, colors, the luminosities, mass to light ratios. And, for a long time, if, things were really great, you could get a velocity dispersion out of a spectrum per galaxy. And, this, and we, people back in the 70s figured out a lot of things about galaxies using just this, So what they found are, galaxies seem to follow these tight scaling relations among their structural properties, so that's the Faber-Jackson relation, the Cormody relation, the fundamental plane. And, and as, instrumentation improved, then these relations started becoming a part of look-back studies, and we could see how things like these scaling relations and luminosity functions changed with epoch and environment. And that really, this stuff that people did, in the 70s, the 80s, and the 90s, into the 2000s, still forms the significant basis of our understanding of galaxy evolution. And and this is all just, pretty empirical, observational, and, what as cosmology developed, and this developed, we, of course, got into the lambda CDM paradigm, and we had to fit this understanding of galaxies into that paradigm, which seemed very sensible at first. But it also led to some questions, why do we end up with such orderly behavior of galaxy properties, given the violent, chaotic nature of the hierarchical assembly of dark matter halos? So that was a little odd. It's kind of a general question that we don't really can't really explain sufficiently. In more recently, stellar population synthesis models, have been developed, Beatrice Tinsley back in the 1980s. And what that has allowed us to do is turn some of these just purely empirical measurements into, things like stellar masses. And what this gives us is a more intuitive way to connect observations with galaxy evolution theory. And, what the field that kind of emerged out of that, the ability to bring those two things together is, how close can we get to predicting what a galaxy is like, just given its dark matter halo, which would be really great if we could do that, because dark matter halos, we can measure them with gravity. So it'd be really great if we could measure just, through, basic dynamics, total mass, and like understand the history of that galaxy. But unfortunately, that hasn't happened. We've, as observations and theory have come closer together, we've, learned that, reality is more complicated than we would wish it to be. And, so this whole field, and there's, the small scale challenges, quote unquote, to land in CDM. And this is one of it. It's just in the black here, we're seeing the prediction of, just galaxy evolution theory of the stellar mass, halo mass, what the halo masses should look like. And then, we're seeing observations in the point, and there's this mismatch. And, the basic point is we need to understand the physics of baryons much better than we do. And okay, great. So, we've moved beyond, just look back studies and scaling relations. Look back studies can be very difficult in just terms of their complicated selection functions, biases in them, stochasticity, are we getting representative physics of them? And so this is where extragalactic archaeology really comes in, where we can try to, deconvolve the present day properties of a galaxy to understand its history. So we're not, archaeological methods aren't subject to the same potential biases that look back studies are. And extragalactic archaeology really got its start when indices, were defined. So the Lick indices were in 1994, getting ages, stellar metallicity abundances out of integrated light spectroscopy of galaxies. This was huge. And, what we learned from these is, so we learned that when we looked at these indices of, massive early type galaxies, we found that they had, very high alpha abundances, and they were very metal enriched, which is unexpected, and that had a mass dependence to it too. And this is what led to what people call downsizing, which is it gave the appearance that the most massive galaxies formed the earliest, which is seemingly in contradiction to Lando CDM. And people, kind of were able to, resolve that by saying, okay, so what happened is formation time is different than assembly time. But then we still don't have a theory of how those stellar abundances make sense. It has to be some rapid early star formation, but we really can't make sense of how you can get so metal enriched given the short time scale that the alpha abundances apply. So this is just, tricky. But indices have their fault. These models are not magic. So the next bit, the big thing is that all these stellar parameters are degenerate with one another. Stellar population synthesis modeling, this was really complicated deconvolution problem. And so, mistakes could be made. And so the next leap forward in SPS modeling were full spectrum fitting and using statistical inference. So indices, you would just do, you'd measure the equivalent widths of one line and another line, and you try to get age sensitive features and metallicity sensitive features and so on and so forth, and maybe like do PCA to combine them and get some, physical properties out of them. Full spectrum fitting, as the name suggests, you're fitting each pixel of the spectrum, and then you're also simultaneously fitting for all those stellar parameters. So what this does in practice is the information that we can get out of an integrated light spectrum is greatly increased. And so for example, just what came out of this is, the measurement of variable IMFs in massive early type galaxies. There were suspicions that these galaxies had variable IMFs before, but it took the development of these full spectrum and statistical inference to actually be able to extract that information out of the spectrum. The problem is that, this actually makes the issues we learned with index fitting worse. If the IMFs in these galaxies are variable, then we know even less. We have even less of an understanding of star formation processes that could have, made this stellar population. And so all of this, I gave this history just to emphasize the first rule of stellar population modeling that's very important, which is garbage in, garbage out. This is a quote from Charles Babbage, who was the person who thought of the adding machine, the precursor to the computer. Kind of like the George Costanza of his time. He was kind of a famous grump. And so on 2 occasions, I've been asked by members of Parliament, pray, Mr. Babbage, if you put into the machine wrong figures, will the right answers come out? I am not rightly able to apprehend the kind of confusion of ideas that could provoke such a question. And this is what I was trying to emphasize going through that history. As we make improvements to stellar population synthesis models, we learn more about these galaxies, and the hope would be that we would clarify some of these things that are confusing from look-back studies and the intersection between extragalactic observational astronomy and our understanding of galaxy theory. But the problem is, it actually has made us more confused. We know even less than we thought. And so just my role in here is moving those full spectrum fitting code and SPS models that were the Conroy and Vendaca models into the metal pore regime. So I can't really get into it. If you wanted to invite me back to give my more star formation talk, my galaxy talk, I can talk more about my specific results for this, which is trying to understand what could be going on with the IMF by looking at metal pore regimes, but also moving into the metal pore, you can start to get stellar population gradients, dwarf galaxies, globular clusters, and I'm going to be talking about some of this that I did in this talk. And of course, this is also expanding the parameter space of these models is also going to help when JWST comes online. And so JWST is going to really be allowing us to combine archaeological methods with look-back studies in just this unprecedented way. But part of what I want to emphasize and what I hope to convince you of in this talk is that this is not going to be a panacea. You know, technical advancements don't overcome the inherent limitations of either look-back studies or stellar population models. So it's something, you know, just being able to get better data at high redshift isn't going to solve galaxy evolution for us. And so that leads me to the two things I'm going to be talking about today. I'm going to try to demonstrate those things with two case studies. I hope I can get to the second one, but we'll see. And so I'll be first talking about the ultra diffuse galaxy Dragonfly 44, which I've subtitled Galaxy Evolution Models in Shoe Leather. And then M87, learning about galaxy evolution with a bunch of lousy globular cluster spectra. And you know, if the eagle-eyed among you might have noticed on my title page that that wasn't a galaxy, that was a globular cluster. I do think globular clusters are the future of extragalactic archaeology. Okay, galaxy evolution models in shoe leather. So I was telling you at the beginning that, you know, back for a long time, we thought there was these very tight scaling relations between, you know, the structural parameters of galaxies. And one of those things was, you know, the size luminosity relation. And so it used to be that we had globular clusters down here, giant ellipticals up here. There was a very distinct separation between star clusters and galaxies, and star clusters were little and they were less luminous than the big luminous GEs, right? But as we've gotten better at observations, this has really introduced a lot of scatter, which we're seeing on here. And particularly controversial addition to this plot has been the ultra diffuse galaxies. What you'll see is on this plot, they have the sizes, you know, Milky Way-like sizes, but then they have dwarf-like luminosities, which is very difficult for us to fit into our framework of galaxy evolution. And, you know, when I talk about this, I want to have you keep in mind that ultra diffuse, what defines that, is completely arbitrary. It's basically objects that were big enough to show up in the Dragonfly imaging, but too faint to show up in SDSS. And it's important to remember that objects that have similar structural properties can have very different formation pathways. And so I should back up and say, you know, originally in the discovery paper Van Dockum 2015, you know, it suggested that these were, quote, failed L-star galaxies because they were large, they were red, they were in a cluster. If they were in a clustered environment and they had to survive for so long, they had to be dark matter dominated. So there had to be something, you know, they had dark matter halos like Milky Way, but for some reason their star formation stopped. And that has been very controversial. And most people, most UDG formation scenarios that have come out have treated ultra diffuse galaxies as contiguous with the dwarf galaxy population, which I'll get into the specifics of that in a bit. But basically, the consensus that is emerging among a lot of the community is that ultra diffuse galaxies, there's nothing special about their galaxy evolution physics. It's just processes that we already know about, oomphed up a little bit. And part of how people have been trying to debate this back and forth is measure dark matter halo masses, right? You know, if we could measure the dark matter halo mass, then we would know what kind of galaxy it is. But first of all, this is specific to Dragonfly 44, which is, it was the largest sample in the original Van Dockum sample. It was, I'm sorry, it's the largest galaxy in the original Van Dockum sample. And so it has had, you know, just massive amounts of telescope time devoted to it. And a lot of that time has been trying to measure its halo mass. And people have done it with GC counts, X-rays, kinematics of the field stars, and it's still very ambiguous. It's very unclear what the dark matter halo mass of this galaxy is. It's unclear what the shape of the dark matter profile is for this galaxy. You know, is it a cusp? Is it a core? We can't tell for sure. And in danger of sounding like a hammer in search for a nail, I don't care what D44's halo mass is. I don't, because I'm more interested in, is there really something about this galaxy that is showing us something we don't know about galaxy evolution? And just trying to measure its halo mass, I think it gets in the danger of our ansats turning into tautologies, right? The presumption behind, if we measure the halo mass, then we would know what kind of galaxy it is not something we know for a fact. And actually, we know there's things that we don't understand, like we don't understand the stellar halo mass relation. You know, that's something we don't know. And so I think the best way to understand these galaxies and their nature is to look at their stellar populations and try to uncover their formation history. And so that's what I did. So for normal dwarf galaxies, stellar population radial gradients are the gold standard to try to understand their formation. Radial gradients probe, you know, the sub-kiloparsec processes that affect galaxy formation. So star formation, feedback, that kind of thing. And so here I'm showing a plot of age gradient versus stellar metallicity gradient. And nearly all of the local group galaxies fall into, you know, this quadrant. They have positive age gradients, and negative metallicity gradients. And one theory of how these gradients and how these galaxies came into being is the outside-in formation scenario. And so star formation started, you know, on the outer bounds and went inwards. Basically, that's what it's referring to. The direction star formation went. And under this scenario, the diversity of gradients, even though they're all in this quadrant, is explained by the longer the star formation has been shut off, the less steep both the gradients get. On the other hand, there's an alternative way to understand this, which is that these the age gradients that they have now were not the age gradients that they had when they formed. That so they formed inside out, so they would have positive metallicity gradients and negative age gradients. And then what happened is they experienced, you know, an extended bursty star formation history that forced stellar migration. And this is kind of the scenario that's come out of the fire simulations. And what this, this stellar migration does is it inverts the gradients to what we see today. And then again, the gradients will get less steep with now late time extended star formation. And so the important thing also to keep in mind is that there's a diversity of dwarf galaxy types. So when people say UDGs are just contiguous with the dwarf galaxy population, it's kind of like passing the buck because we don't know how dwarf galaxies form, but we know some things about them, which is, the local dwarf spheroidals are dispersion dominated, except for this one weirdo, NGC 147, which is rotation supported. And if we go outside of the local group and we look at cluster dwarf ellipticals, which will also be dispersion supported, they are also mostly in the same region of the local group dwarf spheroidals. And if we went and looked at rotation supported dwarfs, so which I'm showing here in black, then we start to see that they have these also kind of distinct gradients. So there's some connection between the stellar population gradients and whether the dwarf is rotation supported or dispersion supported, which makes sense because we think there's some connection between morphological transformations and stellar populations, right? And so I took a spectra that was 17 hours of on-target exposure time on KCWI on Tech 2. This was led by Peter Van Dockum to get the kinematics. And what we ended up getting is the highest signal to noise spectrum of any UDG. Just beautiful data. And so I'm showing you in here what this meant is we could get stellar population gradients because the spectrum, because the signal to noise was so good. And so here I'm showing you the spectrum in black of the integrated spectrum, so that's the full data cube. And then down here, I'm showing the data for the innermost annulus, which was the lowest signal to noise one. And these are the ELF SPS best fit models that I ran. So the fits are very good, the data is exquisite, and so let's look at what the gradients look like. So basically I found pretty much a completely flat zero slope age gradient, and then a slightly positive metallicity gradient. And we know from the kinematic analysis that Peter did that D44 is also pressure supported. So it gets into this weird region of the gradient parameter space. D44 and UDG pressure supported, we might expect them to look like dwarf spheroidals, but that doesn't appear to be the case. Moreover, things are a little ambiguous because of this difficult age gradient, or the flat age gradient. Oh, and this is also important. So, whether or not, or whether the formation happened outside in or inside out, there's no evidence for recent or extended star formation history based off the star population gradients of this galaxy. And also its age is very old, and there's just no, imaging-wise, there's no evidence for recent star formation history either. But to talk about this age gradient and how we can learn more about this galaxy is, I just want to point out that for old stellar populations, there's a limit to how precisely we can discern ages in them. So think about it if somebody asked you to estimate somebody's age based on their height. You'd really be able to, tell the difference between a baby and a kid and a tween and an adult really well based on their height. But once you're all an adult, then age estimates become, far less granular. And it's the same thing with old stellar populations because of the way, the nonlinear way age affects the spectrum. But we also were able to get a magnesium over Fe gradient. And because of the way Fe traces type 1 supernovas and magnesium mostly traces and is produced by type 2 supernovae, magnesium over Fe is a well-known chemical clock. And here we get a very clear negative gradient in alpha abundance for DF44. And if we took that as a more accurate indicator actually of age than the actual explicit age gradient, then we see that DF44 formed inside out. And then the question becomes, well, if DF44 formed inside out, why didn't the gradients invert? How did it become pressure supported without inverting the stellar population gradients? The exquisite nature of this KCWI spectrum also allowed me to take far more precise global measurements of the stellar population parameters. And so here what I'm showing is, in gray, this is the mass metallicity relation for dwarfs, the early type dwarfs from Kirby 2013, coma dwarfs from Smith 2009. And these are, I'm not the first person to try to measure stellar population parameters in UDGs, which I'm showing here in orange, but you can see that the error bars are huge on these measurements. And with the precise measurement that I was able to make, it's very clear that DF44 falls below the mass metallicity relation. And the mass metallicity relation is interpreted as, informative about how star formation both proceeded and, how well a galaxy was either able to keep its metals or actually form its metals. And so this falling below the mass metallicity relation indicates that DF44 didn't have as much time as similarly massed galaxies to enrich in Fe over H. So, which would indicate that its star formation was cut off earlier than other galaxies with its mass. The way satellite quenching usually works, or the way we think satellite quenching works, is that there's a lag actually between when a cluster when a satellite galaxy falls into the dense environment and when that actually turns star formation off. And so this could potentially indicate that there was an unusually catastrophic quenching mechanism for DF44. This is all really just empirical qualitative interpretation of the data, which I think is interesting, but it would also be great if we wanted to understand and really see how, the quenching comparison of DF44 compares to other galaxies, then we really need to measure its star formation history. And it's been, a great pleasure of mine while I've been at Waterloo to be able to advise a couple of students on projects. And I'm about to talk about one of them, which is a project I worked on with Christy Webb, who's a graduating PhD student this year, who is faculty advisor to Michael Ballo. And she's gained expertise in fitting for star formation histories by fitting high Z photometry and spectroscopy together for cluster and field galaxies. And so what we did is we simultaneously fit the broadband SED and optical spectrum to get a star formation history. This is a non-parametric star formation history because we really want to try to determine the quenching time scale, the star formation time scale as well as we can. And there's a lot of details here that I don't need to get into. You can ask me about them later, but it's becoming very well known in stellar population modeling communities that in order to get star formation histories, you really need spectra and broadband coverage that we can only right now get from an SCD. And that's because of the degeneracies that exist between dust, metallicity, and age. Talk about more of that later. And so obviously we had the exquisite KCWI spectrum, but then also, you know, like I said, DF44 has a lot of telescope time devoted for it. So just from the literature, we had near UV photometry to optical photometry. New to this work was near infrared photometry taken by Zeppo Lane at Caltech. Okay, we used Prospector, which is a Bayesian fitting code. You might know it. If you know Josh Spiegel, you probably have heard about this. It uses the FSPS models as its underlying code. Prospector is then just a Bayesian inference on top of those models. And so let's take a look at what we got. All right, so here, you know, I'm showing the photometry, the observed photometry. And then this is the red points are the best fit photometry from the model, from the best fit model. And then here we have the same deal for the spectrum. And so the fit looks really great, in my opinion. And what we find here is that it formed early. It has a relatively short quenching time scale. So we're defining quenching. Just to be aware, quenching time can be defined in different ways. We define quenching time as when 90% of the eventual mass had been formed in the galaxy. So it's old, it quenched pretty quickly, it's moderately dusty. So this is the model we had a diffuse dust component. We're finding that there is indeed dust in it. And we're finding it to be metal poor. And I just want to emphasize that this metallicity is not the same metallicity that I was showing before for the gradients and the mass metallicity relationship, because FSPS and therefore Prospector doesn't fit for non-solar abundances. So we can only get this total metallicity value. We can't get Fe over H, we can't get alpha, so it's different. Okay, but like I said, Prospector is a Bayesian fitting code. Bayesian means prior, right? And so the most relevant prior for this modeling is the star formation history prior, which they can come in like basically two broad categories. The star formation history prior in a non-parametric model controls how the star formation is spread over the time bins. And so here what I'm showing is I used a dispersive star formation history prior. So this would be a prior that favors smooth extended star formation histories, you know, an even distribution among the time bins. And so it's pretty remarkable that even with that smooth prior, that we're still getting a bursty early star formation history. And this dispersive, this might be a technical detail that you don't need to know, but this is the prior that's most similar to what exists in the literature for inversion methods. Inversion methods, Bayesian methods, they have to do this thing called regularization to, make the problem tractable. But, I just spent time telling you from the star population gradients from its location on the mass metallicity relation that DF44 didn't have an extended star formation history. It had an early star formation history. It seemed to have a bursty star formation history. And so we also fit this DF44 data with a concentrated star formation history prior. So then this, dispersive versus concentrated, you can probably figure out what it means. But yeah, this is a prior that then, does favor it doesn't favor anything about which time bins it places the star formation history in, but it favors models that place star formation in a few bins rather than evenly dispersing it through all the time bins. And so I'm holding off on showing you the results, but I'm showing you the fits. And the fits look really good. And then they also look very, very similar to the fits from the dispersive star formation history. So who thinks the stellar parameters are going to be basically the same between these two models with a different prior? Exact same data, exact same model, except for this prior. Anybody think the parameters are going to be the same? No, it sounds like a trick question. Yeah. Well, but actually it is and it isn't. Okay. With this concentrated star formation history prior, well, it's very similar in that it is old, it is metal poor, it is moderately dusty, it has a bursty star formation history, but under this prior, the star formation history is really bursty. So 90% of the stellar mass formed at Z of 8 and then quenched very suddenly. So to me, this is remarkable. These are very different priors, and but even the dispersive star, but they both give qualitatively early, relatively short. One's just much shorter than the other, and moderately dusty, metal poor galaxy. We can't statistically at the moment discern one star formation history over the other. We could make arguments about, which prior is the better prior, and what makes a good prior. And that is a very interesting, but very involved, very tricky piece of research that I would love to spend more time on, but also I don't think it's necessary, since a lot can be said even without breaking this degeneracy.
Wait, Alexa, can I jump in, or would you prefer questions at the end of your talk?
Oh yeah, you can jump in.
So one of the things that I'm wondering about is if you have, so the issue is that the summary statistics are not capturing differences. Obviously, the galaxy knows and the universe knows whether, between these two scenarios, because there is a physical difference between them. So when you plot the sort of subtracted difference between one of these models and the other models, where are you seeing the difference from the, as a function of wavelength in the spectrum? Because I think one of the things that these things point us to is where we actually have to obtain degeneracy breaking data.
Yeah, so this is a really great question, and I'm going to talk about how I think the most efficient way to break this degeneracy is, but it's a really good question. The differences in the residuals is definitely in around the magnesium B line. And so this gets to my point that Prospector, unlike the absorption line fitter ALF, which I did the stellar population gradients, doesn't fit for non-solar abundances. And so, if we were able to fit for alpha and also, fit for Fe over H instead of just Z, then that could possibly be a way to break the degeneracy, because the reason why these the models compared to the data can look so similar is because of the degeneracies between metallicity and dust and age, and there's they can compensate for one another well enough that they can basically give the same best fit spectrum, even though one's a little dustier and one's a little older and less dusty. So
awesome. Thank you. That totally answers my question. Thank you so much.
No problem. I get carried away talking about degeneracies. Okay. Oh.
Is the quenching time scale the same?
Oh, no, sorry. I just didn't even put the blue here because it's just so extreme, the quenching time scale using the Burst star formation history model. It's basically, very quick. So I'm going to talk about how we can use this information to understand whether DF44 is consistent with conventional galaxy evolution. And in order to do that, I kind of have to give you a little primer on what we expect under conventional galaxy evolution. So the big issue I said at the beginning is UDGs have sizes like Milky Way galaxies and luminosities like dwarfs. And while the original proposal was that UDGs could be failed L-star galaxies, the vast majority of the formation scenarios that have come out of cosmological simulations, semi-analytical models have made the claim that UDGs as a whole are contiguous with the canonical dwarf population. And what that means is that you're maintaining the expected dark matter halo occupancies. The stellar mass halo mass relationship is the same. And so you can only adjust either luminosity or size without impacting expected stellar mass. And so even though there's been a lot of papers and a lot of very different different groups trying to come up with formation scenarios, they all kind of come down to the same thing. You can only do so much. There's only so many ways to change effective radius and luminosity without changing the expected stellar mass. And it's tidal interaction, feedback from extended burst star formation history. This was one of the early ones that UDGs are the high-end tail of the halo spin parameter, which expands out the galaxy. And the important thing to keep in mind is that these scenarios that invoke the same or similar mechanisms for redistribution will all have kind of similar expected size, stellar mass, age trends. So just to show you what I'm talking about, if we were going to think about the scenarios that use tidal heating to explain UDGs, so UDGs in the scenario, normal dwarfs go into a galaxy cluster, and through tidal interactions, they're expanded, and their expansion causes them to become diffuse because they're not forming any stars. And so under this scenario, the trend that we would expect is that the earlier quenching times would have the largest galaxies would have the earliest quenching times. There'd be an anti-correlation between quenching time and effective radius, because more time in the cluster means more interaction opportunities, means larger size. And so this is the environmental, the environmental process that could make UDGs. The other scenarios are, the intrinsic scenarios, the high spin parameter. It's an extended burst star formation history. Early mergers that spread out the angular momentum of the gas. In this case, the size would increase with later quenching time, which would be expected from normal growth. Oh, and I'm sorry, let me back up. This is a plot showing various predictions from different from the fire simulation and then the Romulus C simulation from Tramal. These points here in the Tramal simulation, they're tracking what looks to be like UDGs that were formed through this tidal interaction. And then here in yellow, I'm showing from the fire simulation how they explain UDGs through extended burst star formation history. And there's a couple things to really notice, which is, and they're highlighted in this yellow, which is that the higher mass galaxies have to quench early because anything else would violate the luminosity constraints that are inherent to UDGs. So this is the trick with these other formation, the non-environmental formation scenarios, is there's this very tight balance between how much star formation you can make, how big you can get that with the mechanisms available to you, and when that all happens. So you can see that in here, it's the high mass galaxies are the smaller, earlier quenched ones, and then the less massive UDGs are the later quenched, larger galaxies. And under these scenarios, this extended burst star formation feedback, they're never going to be able to make galaxies as large as DF44. Remember that I said that DF44 is the largest UDG in the original Ben Dockham sample. And this is tricky because the particulars of different models will give different predictions for structural parameters. And so, these are the Trammell points from tidal heating that expand to tidal heating. And then these are tracing a different formation. This is cosmological simulations, those things are complicated. It's not just one thing, it's all of them interacting together. And so larger sizes mean later formation times, because again, it's this constraint that between the luminosity and the radius that is very tricky. I'll just avoid that point. Okay, so now, here's DF44 on this plot now. So here is where DF44 lands using the concentrated star formation history prior, and here's where DF44 lands using the dispersive star formation history prior. And so obviously, if we were looking at the concentrated star formation history prior, there'd be no doubt, right? It'd be obvious that none of these formation scenarios work for DF44. But it's not, there's some plausibility for the dispersive star formation history prior. But this is what I mean when I said galaxy evolutions in shoe leather, which is people try to, there's this issue of we have to slice through particulars of parameter space when we're comparing our empirical measurements from observations to galaxy evolution theory, but that isn't sufficient. Plots like this are not sufficient to totally determine one formation scenario from another. The thing that's missing from this plot is, of course, that we know that DF44 formed early and quickly. So it kind of is in opposition to the late formation times that would be necessary under this scenario. Otherwise, it could be the tidal interaction scenario, which would require early infall. It would require DF44 to fall, early into Coma cluster, but the preponderance of evidence from phase-space diagrams to looking for evidence of tidal tails and coma UDGs indicate actually that DF44 was a late infall into the coma cluster, which suggests that the cluster environment is not what quenched DF44, which is very different than expectations of how we think galaxies of this mass can quench. We think they must have to be quenched by environment. And so, like the stellar population gradients, like its placement on the stellar metallicity mass relationship, DF44 does not appear to be consistent with expectations of conventional galaxy evolution. And there's been suggestions in semi-analytical models of what could be causing this. In my gradient paper, I suggested that it was a strong single burst of feedback that created the original stars, its globular cluster populations, and also quenched. And this was something that Shani Dinelli also explored in actually using a model, the Sebastian Trio Gomez's model, to show what this would look like for NGC 5846 UDG1. But the problem, I'm wrapping up, I swear. The problem is that these are only semi-analytical models, and cosmological simulations, if they worked, would be the ideal way to try to understand what was going on with DF44. But the problem is that cosmological simulations can't even get sizes for the compact dwarf population. This is a summary figure from Jiang 2019 going over that. It's just comparing, it's basically just showing that various simulations over-predict the sizes of dwarfs. And this is something we see in Trammell. This is something we see in the fire simulations. And so what we're saying when we say, maybe it's this intense feedback episode that's quenching this galaxy is making their issues even worse. Or we're missing a potential quenching mechanism entirely. So I'm going to wrap this up because I know I'm over time. But basically, it's really important that we actually be able to constrain the when and the how quickly of the quenching. We do have to do better than what we currently have in order to help guide the galaxy evolution models of what they could be missing. And I'll just end on this, and anybody who is interested can ask me later. But basically, because of the degeneracies and how they work, I think getting mid-infrared data from JWST would be a fantastic way to help break this degeneracy. So, questions?
Thank you, Alexa, for the talk. Are there any questions? Maybe we can start from online. Feel free to just speak up. Raise your hand. See something? No. All right. What about in person? Oh, okay. We have a bunch of questions in person. So sorry, people online. Let's start with.
I was just going to ask, in the concentrated star formation mechanism, is there something about that that's pushing, something about the prior that's pushing star formation to like the very highest redshift bin? Is there something special about that it's peaking in the highest redshift? Or
No.
it peaks somewhere?
No. So these star formation history priors, they don't put any prior information on when star formation happens. And so that's what makes up, especially the dispersive star formation history prior so interesting, that it still kind of recreates this bursty star formation history. What was I going to say? That interesting thing, though, is that the dispersive star formation history actually places a prior against very old ages in a way that the concentrated star formation history prior doesn't. In that sense, the concentrated star formation history prior is a less informative, less constraining prior than the dispersive star formation history prior.
Thanks.
Yeah, coming back to dark matter, sorry. So I don't know the exact numbering here.
Well, like I said, the measurements are very ambiguous. If you used the Van Dockum 2019, which was kinematics of the field star population itself, about the dark matter halo mass is 10 to the 11 solar masses with a huge error bar, and we can't constrain the shape of the dark matter halo, which contributes to the uncertainty. If we looked at the GC counts and used GC scaling relations, then the dark matter halo would be, you know, higher than that. So that's the point, is like the dark matter halo is very ambiguous, and so we should look toward the actual star populations to see what's going on in it.
Second question, unless there's some other one. I'll hand it over.
Relay. Hey, Alexa, last plot you showed, right, with the JWST, population synthesis models, and you were like, and look how great the mid-infrared would be in breaking through all these degeneracies. So I'm wondering, can you kind of walk me through this? Because
yeah, definitely, for sure. So yeah, now we're measuring, we're measuring some dust, right, in DF44. But if you notice here, the dispersive star formation history is a younger age than the concentrated star formation history prior. You know, understand what you'd expect. But then it has a higher dust content, the dispersive one, compared to the concentrated star formation history prior. What happens? It's so great, and particularly the near UV. So what's going on is that, so here we're seeing the formation history, this last 100 megayears, and we see that also in the concentrated star formation history case. That is almost certainly not actual star formation happening. Almost certainly contamination from blue horizontal branch stars. We can't fit with our star population models yet, another limitation. But in either case, this is information coming from the system. There's some hot population in DF44, whether it's blue horizontal branch stars or like a genuine young population. So, you know, hot stars, right? They increase, you know, the flux in the blue and the near infrared, or I mean, the near UV. But because we have constraints from the, we actually have points in the near UV, we know that it can't, there has to be something that is bringing down that flux that we would expect to be getting from the whatever this hot population of stars is. There has to be dust. But the way it works is the dispersive star formation history prior, it can't get as old as the concentrated. That's what I was saying in response to another question. It is actually completely disfavors by nature very old star populations. And so the model is getting more of this hot population, but the constraints are the exact same. So then the model has to add more dust to the model in order to match both the spectra and the near UV photometry. And so the concentrated star formation history prior doesn't have to add much dust because it's allowed to have older ages, and so less dust is necessary to match both the photometry and the spectroscopy. What I was saying with JWST is that, you know, there's the degeneracy between age and dust. The age and dust is degenerate over the near UV and the optical and the near infrared, but going to the mid infrared would actually allow us to place more constraints on the diffuse dust content in this galaxy, which you can see between the blue line and the purple line. The blue line has a dust contribution, the purple line doesn't. You see that they're the same, these two models are the same over the near UV to the near infrared, and then they're very different in the mid infrared. Constraining the dust mid infrared photometry would necessarily mean that we're able to down formation history in the age better, because that's contributing to the degeneracy. And so with Juna's question, I think this is actually the easiest thing we could do to get the degeneracy. Like, I'd love to develop SPS models that fit formation histories and non-variable or non-polar abundances, but that's a lot of work. That's going to take a lot of time, and I think we can make a huge progress just data.
Oh, okay. So that's a very detailed, good explanation, which kind of went over my head. So I'm trying in kindergarten, Bob, and tell me if I'm getting it right. Which is, so you got in this thing, and it is absorbing light, ultraviolet energy's got to go somewhere, and so it get re-radiated in so pH. So the problem we had was this age dust degeneracy. You're breaking it, right? Because you just figured out that it's got to be dust.
Yeah.
Okay,
Exactly.
Okay, I got it. Cool.
You have a question from the internet. Who can unmute yourself and ask the question? I see you have your hand raised.
Yes, thank you. I hope you can hear me well. The connection is a bit
So fine.
noisy on this end. But I guess I would urge you not to consider. Hello, Alexa. First of all, sorry, a great talk. I guess I urge not to consider DF44 as a particularly, unique galaxy that requires a unique explanation. I mean, it's true that these ultra-faint dwarfs in coma appear to be outliers, but only that's because you compare them to the most well-known, giant ellipticals, which are of course much denser, and the dwarf ellipticals, like I say, M32 or so. But if you compare them with populations of galaxies that are very well known, like low surface brightness, dwarf irregulars, they're actually very similar. For example, there's a bunch of those for dwarf irregulars. These have spinning disks and are forming stars today that have similar stellar masses and similar velocities and similar sizes as well. So they don't appear to be particularly different from them. It's just that appears that in coma, we have this population which look like dwarf irregulars, but they're not forming stars. And until now, until your discussion here, I thought that what distinguished them was that they had very old stellar populations. But if that's not even that is true, then they even look more like dwarf irregulars, just without the spinning disk and without ongoing, at least massive star formation today. So maybe they don't need any particular, relatively, dramatic or unique explanation for the formation of these objects. It's just, the tail of the distribution, like the low surface brightness galaxies always have been.
Well, excuse me if I didn't say this clearly enough, but I mean, you're saying they're very similar to dwarf irregulars. And I would say that they're very similar to dwarf irregulars, except that they're dispersion dominated, but somehow their stellar population gradients didn't invert. You know, what explains that? There actually are very old stellar populations like that. DF44 very clearly has a very old stellar population that formed quickly and quenched. The question is how early, how quickly, more precisely, like is DF44 old or is it really old? And that makes a difference in the different formation mechanisms. And so I'm not sure I understand your point about how they're similar to dwarf irregulars.
I mean, my point was more of a comment, really. I mean, like, just a historical note, you know, dwarf spheroidals used to be considered very different to dwarf irregulars until people discovered that were kind of similar, except that one seemed to have, you know, an ongoing star formation because of the presence of gas. But in everything else, their metallicities, their sizes, their overlord potential wells, they all are very, very similar. And this, I think, is the same issue. I mean, no, they're not the same, clearly, but they're not that different. So in other words, you take a dwarf irregular of the same size and same velocity, you take out the gas and the ongoing star formation, it won't look too different, right? Dwarf irregulars, they have some rotation, but they're not dominated by rotation. If you take out the gas and the young stars, I would say they're not dominated by rotation. Of course, the gas is dominated by, and the star forming gas is dominated by rotation. But if you go into coma, take out that gas, it won't look so different. And if you merge, if you maybe make them entirely interact, that will mess up a little bit the internal dynamics, and you'll end up with a spheroid that doesn't look too different. So I guess there may be explanations that don't require any particular particularly difficult or different scenarios to explain them. It's more a comment. I guess it wasn't a question to you. I mean, I appreciate what you've done.
Well, maybe we should continue this more after the talk, because I'm just not sure I'm getting exactly what you're saying, because to me they are very different in many ways than the canonical dwarf population, and so I think maybe we're not communicating effectively with each other. So I'd be happy to, I'm here tomorrow too. So, if you want to talk more about this, I'd be really happy to, because maybe I am behind on all the dwarf formation scenarios. So I'd like to hear more.
Yeah, sure, of course.
Thank you for the nice discussion and conversation. Let's thank Alexa again. We are 15 minutes late.